The Karapiro Gully Viaduct, a remarkable engineering marvel, is set to become a significant landmark in New Zealand's Waikato region. This impressive 200-meter-long bridge is situated on the Cambridge section of the Waikato Expressway and has been constructed to ease congestion and reduce travel time for commuters through the area. The viaduct's imposing structure and visual appeal have captured the attention of the nation. The bridge stands tall at a height of 40 meters, rivaling the iconic Auckland Harbour Bridge in magnitude. Its design incorporates 3 piers and 4 spans, with a total of 4,110 steel pieces meticulously assembled using approximately 23,500 bolts. Notably, the Karapiro Gully Viaduct is the largest bridge to be constructed as part of the massive $2.1 billion Waikato Expressway project. One of the most fascinating aspects of this viaduct is its unique construction materials. Unlike traditional steel bridges that require regular maintenance and painting to prevent rust, the Karapiro Gully Viaduct is built using weathering steel. This choice was made due to the challenging access and considerable height of the bridge from the ground, which would otherwise create maintenance difficulties. Weathering steel boasts a design life of over 100 years and demands very little maintenance, making it a cost-effective and long-lasting solution for this ambitious project. As the viaduct nears completion, the final touches are being put in place. The foundations, substructure, superstructure, expansion joints, handrails, and drainage have all been successfully completed. An asphalt leveling course has been installed, providing a waterproofing layer to protect the bridge's deck from water damage before the final road surface is laid. Beyond the impressive engineering feats, the project also demonstrates a commitment to environmental conservation. An extensive vegetation restoration program is underway on the gully floor below the bridge. Over 49,000 trees and plantings, predominantly native species such as manuka, karamu, and kanuka, are being planted in the gully. Wetland plants like cabbage trees and flax are being cultivated along the Karapiro stream, while additional trees have been strategically placed to create a habitat for bats. The Waikato River Bridge is a significant infrastructure project aimed at integrating the Peacock area into the city of Hamilton and the wider region. The project, with a budget of $135 million, encompasses the construction of the bridge and an extensive surrounding transport network. The bridge itself boasts 4 lanes, with dedicated bus lanes to enhance public transportation. Additionally, separate paths for pedestrians and cyclists ensure safety and convenience for non-motorized travelers. Spanning 110 meters over the Waikato River, the bridge's unique design features a single Y-shaped pillar on the south bank, supporting a flat bridge deck stretching over 200 meters without any piers in the river. This innovative approach minimizes environmental impact while maintaining functionality. The surrounding transport network enhancements play a crucial role in connecting Peacock to the rest of the city and accommodating future growth. An extension of 1.6 kilometers to Wairiri Drive, urban upgrades to Westonleigh Drive and Peacock's Road, and the prioritization of buses and public transport through underpasses and separated bike paths ensure efficient and accessible transportation options. The Ren Metro Viaduct, a remarkable feat of engineering, is a pivotal component of Line B within the Ren Metro network. This extraordinary viaduct is currently under construction, undertaken by Iphigenia Civils teams in consortium. As of mid-September, an impressive milestone was achieved, with 50% of the decks, 1,200 meters, already successfully completed. What sets this structure apart is its non-standard design, featuring bend radii of 125 meters. It is also the first ever project globally to utilize a launching beam technique, enabling the simultaneous suspension of 2 spans, a groundbreaking achievement in the field of construction. The viaduct boasts an impressive 70 piers, varying in height from 4.5 to 9 meters, and it will support a total of 34 double-span decks and 2 single-span decks, which will be constructed using 973 arch segments. To realize this ambitious project, a massive amount of construction materials will be utilized, including 28,000 m³ of concrete, 4,000 tons of reinforcement, and 5,300 square meters of BSI concrete side shields. The inception of this engineering marvel dates back to October 2015, following 18 months of meticulous preliminary studies and technical development. The entire project is anticipated to be completed by the early summer of 2018, ensuring an efficient and modern addition to the Rennes metro network, benefiting countless commuters for years to come. The Yavuz Sultan Selim Bridge, also known as the Third Bosphorus Bridge, is an architectural masterpiece that spans the majestic Bosphorus Strait, connecting the European and Asian sides of Istanbul, Turkey. Named after the 9th Ottoman Sultan, Selim I, this engineering marvel is not only an essential transportation link, but also a symbol of Turkey's ambition and progress. Designed by the Swiss engineer Jean-François Klein and the French structural engineer Michel Virlogeau, the bridge stands tall as one of the world's tallest and widest suspension bridges, embodying the country's commitment to modern infrastructure development. This article delves into the construction process, key features, challenges faced, and its significance in connecting communities and enhancing the nation's economy. The foundation stone laying ceremony for the Yavuz Sultan Selim Bridge took place on the 29th of May 2013, with great enthusiasm from the Turkish people. Its location to the north of the existing 15th of July Martyrs Bridge, First Bosphorus Bridge, and Fatih Sultan Mehmet Bridge, Second Bosphorus Bridge, was carefully chosen to ease traffic congestion and improve connectivity between the European and Asian parts of Istanbul. At an impressive height of 322 meters, 1,056 feet, the Yavuz Sultan Selim Bridge ranks among the tallest bridges in the world. It also holds the distinction of being the 5th tallest bridge globally, regardless of type, with a width of 58.4 meters, 192 feet. It is one of the world's widest suspension bridges, allowing ample space for both rail and motor vehicle transit. The bridge forms a crucial part of the ambitious 260-kilometer, 160-mile Northern Marmara Motorway, also known as Kuzi Marmara Otoyolu. This motorway project aims to bypass urban areas of Istanbul in the north and connect Kanali and Silivri in the west to Pasakoy and Hendik in the east. As a combined road-rail bridge, it accommodates 4 motorway lanes and 1 railway track in each direction. The bridge's length measures an impressive 2,164 meters, 7,100 feet, with the main span extending 1,408 meters, 4,619 feet. This main span is the 13th longest suspension bridge span in the world, a testament to the ingenuity of its designers and engineers. The construction of the Yavuz Sultan Selim Bridge was a monumental undertaking that required precise planning and execution. A consortium comprising the Turkish company İKTİZ and the Italian company Astaldi won the bid to construct the bridge on the 30th of May 2012. The estimated cost of the entire project was around 4.5 billion Turkish lira, approximately 2.5 billion United States dollars as of March 2013, making it one of the largest infrastructure projects in Turkey's history. Originally scheduled to be completed in 36 months, then Prime Minister Recep Tayyip Erdogan challenged the construction management team on the 29th of May 2013 to finish the project within 24 months, setting an ambitious opening date for the 29th of May 2015. Despite the challenging deadline, the project team worked tirelessly to meet the expectations of the nation and complete the construction on time. However, as with any major infrastructure project, unforeseen challenges arose during the construction phase. The Turkish currency and debt crisis in June 2018 impacted the project significantly. Astaldi, in partnership with Webuild, an Italian multinational construction company, sought to sell its stake in the Yavuz Sultan Selim Bridge project for $467 million due to underwhelming revenue projections. Consequently, Ankara had to step in and provide additional financial support to boost the operator's revenue from the treasury. The Yavuz Sultan Selim Bridge holds immense significance for Turkey, both economically and socially. For over 5 decades, Can-Am Pont has established itself as a prominent player in the North American market, excelling in the design, manufacturing, and construction of steel bridges, expansion joints, and bearing devices. Their position as a leader is attributed to their exceptional team, state-of-the-art facilities, and unmatched expertise in the field. The metallization process. Corrosion protection, one of the key aspects of Can-Am Pont's success, lies in their effective use of the metallization process. Metallization involves the application of a 5% zinc coating on steel components to provide robust protection against corrosion. This protective layer acts as a barrier, shielding the steel from contact with moisture and preventing oxidation. Metallization is particularly effective in humid and saline environments, where corrosion poses a significant threat to steel structures. Electrochemical reaction and benefits. Metallization leverages an electrochemical reaction between the steel and zinc, offering an additional layer of protection to the underlying structure. When the zinc layer gets damaged, it sacrifices itself to protect the steel, similar to the benefits provided by zinc-rich coatings and galvanization. The key advantage of metallization over galvanization is that it mechanically fixes the protective layer without subjecting the steel to significant thermal effects. This makes it an ideal choice for large steel beams, ensuring their structural integrity is preserved. Electrochemical reaction and benefits. Efficient application process. The metallization process is carried out using an arc spray gun, which applies a mixture of melted zinc, aluminum, or other equivalent metals onto the steel surface. The tiny molten metal droplets cool and harden rapidly, forming a durable protective coating. Prior to metallization, the steel surface undergoes preparation using abrasive jets to create an ideal angular profile, ensuring the coating adheres effectively. Immediate manageability in environmentally friendly. Metallization is a cold process that requires no drying time, enabling immediate handling and significantly increasing the manufacturer's production capacity. Furthermore, the process is environmentally friendly as it does not emit volatile organic compounds, allowing excess materials to be recovered and reused. Additionally, the thermally sprayed coating demands minimal maintenance, even in extremely dirty environments, reducing long-term maintenance costs. Bolted assemblies and safety measures. In the construction of steel bridges, bolted assemblies play a crucial role in ensuring structural stability. To counter varying loads, impacts, vibrations, and potential slipping, anti-slip type connections are employed. Engineers meticulously determine the coefficient of friction between assembly surfaces to accurately calculate resistance to slipping and guarantee the structure's integrity under service loads. Can-Am Pont places the safety of its employees at the forefront of its operations. For metallization, they prefer an alloy consisting of 99.9% zinc, rather than a compound of 85% zinc and 15% aluminum, providing a more economical, yet equally effective solution. Before we delve into the construction of the Brunstabel Bridge, let's explore its history. The bridge's origins trace back to 1792, when the first wooden structure was built, followed by a steel truss bridge in 1938. Tragically destroyed during World War II, it was reconstructed in 1948-49, symbolizing resilience and community spirit. The Brunstabel Bridge, located in Vorarlberg, Austria, has a rich history dating back to its first construction in 1792. Over the years, it has undergone significant changes, with its original wooden structure giving way to a steel truss bridge in 1938, followed by a reconstruction in 1948-49. Each phase of its construction holds a story of resilience and adaptability, reflecting the importance of this vital transportation link between Doorn and Krumbach. The first iteration of the Brunstabel Bridge was built in 1792, under the leadership of Johann Georg Vogel. This wooden bridge was covered, had 3 spans, and spanned a length of 26.5 meters. Although it served its purpose at the time, the bridge was narrow, measuring only 1.9 meters wide, and could accommodate only a single horse-drawn vehicle. The inscription 17 G M 92 inches carved into the timber represented Master Georg Maurer, who hailed from Riefensberg. In 1910, the bridge faced extensive damage during a flood disaster, prompting significant repairs as part of the state's construction program. Unfortunately, the bridge's fate took another unfortunate turn during World War II when it was demolished by the Reich Labor Service on July 20, 1940. After the destruction of the wooden bridge, a steel truss bridge was constructed between 1937 and 1938. This new structure stood tall over the Weisack River, soaring to a height of 40 meters and spanning a length of 116 meters. The bridge's design, crafted by the construction company Wagner Biro from Graz, utilized massive double T girders. However, due to the scarcity of resources during World War II, the bridge's construction had its limitations. The roadway, with a width of only 5 meters, could only be provisionally covered with wooden planks, allowing for a maximum load of 12 tons. These wooden planks were installed by the master carpenter Jodoque Troy. Tragically, the steel truss bridge faced a premature demise when fanatics from the Nazi Wehrmacht blew it up on April 30, 1945, only a few years after its completion. The explosion's shockwave was so intense that it shattered windows in nearby farms. Undeterred by the destruction, the local community persevered, utilizing the debris from the collapsed bridge as construction material for another bridge between Langenegg and Muselbach in 1947. Despite the setback, the severed transportation link between Doren and Krumbach needed to be re-established. The reconstruction of the Brunstabel Bridge commenced in 1948, using the surviving pendulum supports from the previous bridge. This time, a new frame structure was added to strengthen the bridge's integrity. The roadway width was expanded to 5.5 meters, and cantilevered sidewalks were installed on both sides, ensuring safer pedestrian passage. The state of Vorarlberg took full responsibility for funding the reconstruction, investing 900,000 shilling in the project. After months of hard work and dedication, the bridge was completed and ready to serve the community once again. On a momentous day, Sunday, October 16, 1949, the newly reconstructed Brunstabel Bridge was inaugurated and officially opened to traffic by the esteemed priest Gavinesh from Krumbach. Since its reconstruction, the Brunstabel Bridge has stood as a symbol of resilience, representing the determination of the people to overcome adversity. Through the years, the bridge has seen the evolution of transportation and engineering, reflecting the changing needs and capabilities of the region. As a crucial link connecting Doren and Krumbach, it continues to play a vital role in the lives of those who rely on its existence. The planning firm Schimmeter took on the responsibility of designing the new bridge. The result was an impressive 3-span concrete structure with spans of 38, 51, and 38 meters, providing a total span of 127 meters. The cross-section of the bridge was carefully thought out, incorporating plate girders with a variable height of 2 meters in the field and 3.5 meters at the piers, and a total width of 10.5 meters. This design would ensure the bridge's stability and longevity while accommodating the traffic demands of the region. With the design in place, the Vorarlberg state initiated a public tendering process to select a competent construction company. The company Wilhelm und Mayer emerged as the best bidder and was awarded the construction contract. In September 2013, the construction phase commenced, marking the beginning of a project that would require a significant amount of expertise, ingenuity, and perseverance. One of the most challenging aspects of the project was laying the foundation for the 2 new bridge piers. These piers had to be constructed outside the riverbed, on the steep slopes on the left and right of the Weisack, upstream from the existing supports. Accessing the foundations proved to be a daunting task, necessitating the construction of a steep access road along the left bank of the river and an additional construction road to reach the Doren support on the right bank. To ensure the stability of the bridge, deep-drilled shafts called Brunnenlead Pfeiler were utilized. These shafts, reaching depths of up to 9 meters, were constructed using shotcrete, a method that involved spraying concrete onto the foundation to create a sturdy base. The decision to anchor the foundations in bedrock minimized the risk of disturbing the riverbed and added an extra layer of safety to the project. Throughout the construction process, the project team encountered various challenges. The ground conditions were far from ideal, posing difficulties during foundation work and construction. Additionally, the limited construction space demanded precise coordination and careful planning to ensure the safety of workers and the public. Furthermore, an ambitious construction schedule put pressure on the team to deliver the project within the stipulated timeframe. However, the team rose to the occasion, tackling each obstacle with determination and resourcefulness. With innovative construction techniques, such as the use of formwork climbing systems for the tall piers and the implementation of anchoring with injection and micropiles for stabilizing the slopes, the team navigated through the complexities of the project. Once the main bridge span and approach ramps of the Brunstabel Bridge were firmly in place, the construction team turned their attention to safeguarding the structure from the unforgiving elements. The bridge's longevity and structural integrity depended on its ability to withstand the adverse effects of weather, particularly the moisture from rain, snow, and humidity. High-quality waterproofing materials were applied to the bridge deck and other vulnerable areas, creating a protective barrier that would prevent water from seeping into the concrete or steel components. Expert asphalt paving crews carefully laid down a thick, uniform layer of asphalt over the bridge deck. The asphalt was then compacted using heavy machinery to create a seamless and even road surface. This process was crucial to ensuring a comfortable driving experience for commuters, minimizing vibrations, and allowing vehicles to glide smoothly over the bridge. In a remarkable display of engineering prowess, the construction site in Phil Campbell, Alabama, witnessed the impressive feat of lifting 120,000 lb, 54,431 kilogram, bulb T-bridge beams 120 feet, 36.5 meters into the air using state-of-the-art Link-Belt cranes. The two cranes responsible for this task were the Link-Belt 248 HSL, a 200-ton, 181.44 mt lattice crawler crane, and its companion, the 248 H5, designed specifically for heavy lifting, capable of hoisting up to 135 feet, 41.1 meters. Phil Campbell, a town known for its natural beauty, was set to witness the creation of a vital bridge overpass, which would improve connectivity and facilitate smooth transportation for the region. Link-Belt's 248 HSL and 248 H5 cranes, known for their reliability and precision, were the ideal choices for this complex and challenging task. The 200-ton, 181.44 mt lattice crawler crane, the 248 HSL, is a powerhouse, perfectly suited for heavy lifting projects. Its robust construction and cutting-edge technology allow it to handle massive loads with ease, making it the go-to crane for such demanding construction tasks. The 248 H5, on the other hand, was tailored to handle high-capacity lifts with a maximum reach of 135 feet, 41.1 meters. The bridge beams, weighing an astonishing 120,000 lb, 54,431 kilograms, posed a unique challenge, but the 248 H5 proved to be more than capable of meeting it head-on. Its advanced hydraulic system and intuitive controls allowed for smooth. Coastal Highway Route E39, stretching from Kristiansand to Trondheim in Norway, is a nearly 1,100 kilometers long route that currently relies on 8 ferry connections to cross various fjords along the coast. However, there is a growing interest in establishing a more efficient corridor with permanent links, eliminating the need for ferry crossings. To achieve this ambitious goal, the Norwegian Public Roads Administration has initiated a technological development project to explore the challenges and social impacts of creating a ferry-free road connection along the E39. One of the significant challenges lies in crossing the wide and deep fjords of western Norway. While the less complicated fjord crossings have already been built, the extreme fjord crossings require cutting-edge technological advances. The Sandfjord in particular presents a prime example of these challenges due to its immense width and depth. To bridge this fjord effectively, it must be viewed as a way of joining the two banks rather than a barrier. The Sandfjord measures 3.7 kilometers wide and 1,300 meters deep. necessitating a bridge significantly longer than any existing structures. To accommodate unhindered passage for ships, a shipping lane at least 400 meters wide, 70 meters high, and 20 meters deep is required. 5 different bridge designs are being considered for this endeavor. The first option is a suspension bridge, a traditional solution for such crossings. A suspension bridge across the Sandfjord would need a main span of 3,700 meters, almost 3 times the length of the Golden Gate Bridge in San Francisco and twice the current world record length. The 2 bridge towers would reach an impressive height of 450 meters. Another alternative is a floating bridge, similar to the world's longest bridge of this type, the Nordhordland Bridge. However, building a floating bridge across the Sandfjord is even more challenging due to its depth, making lateral anchoring difficult. Ensuring sufficient rigidity and allowing enough clearance for ships are among the primary obstacles. A novel concept being explored is a submerged floating tunnel, consisting of 1 or 2 concrete tubes submerged approximately 20 meters below the fjord's surface. Anchoring such a structure at these depths poses a unique challenge. The submerged floating tunnel can also be combined with a floating bridge to create an unprecedented design that allows unrestricted sailing height for ships. Additionally, the traditional cable stay bridge is considered as an alternative. With towers built on floating elements, this idea draws inspiration from the offshore industry's large platforms anchored in deep water. However, implementing this concept for bridges is uncharted territory. While the technical feasibility of bridging the Sandfjord may be possible within a few years, the decision to proceed with construction remains a political question. The project's success will require a substantial commitment of resources and careful consideration of the environmental and social impacts. Moreover, the solutions explored for the Sandfjord crossing could have implications for other fjord crossings along the E39 and elsewhere in Norway. As the project continues, it will be crucial to balance the need for improved transportation infrastructure with the preservation of Norway's stunning natural landscapes and delicate ecosystems. The 890-meter-long Norjang Bridge is the 3rd longest bridge in the country, following the Yi-Sun-Sin Bridge, 1,545 meters, and Ulsen Bridge, 1,150 meters. The inclined main tower stands tall at 140.86 meters and enhances structural efficiency by tilting the angle of the pylon by 8 degrees. The inclined main tower stands tall at 140.86 meters and enhances structural efficiency by tilting the angle of the pylon by 8 degrees. This inclination enables better balance and maximizes the tension of the main cable between the main span and the measurement. The base of the pylon is designed to support an extraordinary load of 42,000 tons, utilizing a 50-meter wide, 30-meter long, and 8-meter high concrete direct foundation. To ensure stability, the construction team excavated the hard rock section without defects to a depth of more than 30 meters and divided it into 4 sections, each 2 meters in height. The inclined main tower stands tall at 140.86 meters and enhances structural efficiency by tilting. The construction of the pylon employed an auto-climbing system that allowed for changes in the shape of the cross-section and the angle of inclination. With this system, the workers placed concrete in 37 sections, each 4 meters in height. The amount of slope was meticulously calculated using precise engineering, and GPS-based site surveys were conducted to establish the installation coordinates of the formwork for each section, ensuring accuracy and precision throughout the construction process. The Norjang Bridge was intentionally designed to form a V-shape, symbolizing openness and a welcoming embrace of Halihøysand National Park, in commemoration of King Chungmugong's remarkable victory of 23 consecutive wins. The anchorage of the bridge is robust enough to support the weight of approximately 50,000 vehicles, equivalent to 35,000 mid-size passenger cars. This 3,000-ton concrete structure effectively supports the main cable, which is under a force of 13,000 tons. Throughout the construction process, concrete was poured 15 times, with each pour reaching a height of 2.1 meters. In total, 7,300 cubic meters of ready mixed concrete were used, generated from the mass concrete of 400 tons of ready mixed concrete during each casting. To control the heat of hydration, a pipe cooling method was employed. Additionally, the concrete part where the main cable is fixed was reinforced with the installation of pipes, and strand wires were inserted into these pipes to apply compressive forces corresponding to the tensile forces, ensuring the safety and integrity of the structure. One of the most innovative aspects of the construction was the use of the widening 3D cable method for the main cables of Noryang Bridge. This technique involved gradually spacing the cables from the main tower towards the center of the bridge, optimizing the placement of the anchorage and maximizing wind resistance. To facilitate the installation of the cables, a temporary structure was erected after the completion of the main tower construction. This structure provided a stable platform for workers to lay the main cables, ensuring precise alignment and enhancing the overall strength and stability of Noryang Bridge. The 890-meter-long Noryang Bridge is the third longest bridge in the country, following the Yi Sun Sin Bridge, 1,545 meters, and Ulsan Bridge, 1,150 meters. GSE&C, the company behind this remarkable construction, utilized their technology to create the V-shaped main towers, which reduced the tension of the main cable and represented the victory of Admiral Yi Sun Sin. Moreover, the company used 3D cables, a first for a suspension bridge, arranged in a streamlined shape to increase wind resistance. The significance of Noryang Bridge goes beyond its engineering marvel and architectural beauty. It is located at the site of the Battle of Noryang, a historic naval battle in 1598 where the combined fleets of the Joseon Kingdom and Ming Dynasty fought against the Japanese Navy. This historical context adds a deeper layer of meaning to the bridge, making it not only a symbol of modern engineering prowess, but also a tribute to the valor and bravery of the past. In the construction of the Noryang Bridge in the Gwangyang area, a significant aspect was the installation of 8,500 tons of reinforcement girders. These girders were precisely manufactured at a dedicated steel bridge manufacturing plant and were divided into 45 blocks to facilitate transportation and assembly. The C-section of the bridge was accessible by barges, allowing for efficient delivery of the girders to the construction site. To lift the girders vertically from the barges and assemble them into position, a sophisticated lifting device was employed. This device ensured precision and safety during the installation process. However, the central part of the bridge posed a challenge as the low height of the main cable made it impossible to use the standard lifting device. To address this, a massive 1,200-ton offshore crane was utilized. This powerful crane was capable of lifting and positioning large 45-meter-long blocks, overcoming the height restrictions imposed by the main cable. For the main cable itself, it was crucial to ensure resistance to corrosion and maintain its structural integrity over time. To achieve this, an S-shaped wire was used with a thickness of 3 millimeters and a width of 7 millimeters. This specific wire design minimized the risk of corrosion, ensuring the longevity of the bridge. To provide an additional layer of protection and durability to the main cable, the surface was tightly wrapped using a wrapping machine. This wrapping process not only safeguarded against potential corrosion, but also enhanced the cable's structural stability. The top plate of the bridge was designed to include an epoxy and pavement layer, serving as a waterproof coating. This layer acted as a barrier against water infiltration, preventing any potential damage caused by moisture and environmental elements. The epoxy and pavement layer further contributed to the overall robustness of the bridge's structure.